Benjie, are you with us?
I'm with you. Thank you, everyone.
Great.
Hello.
Great. How's it going?
Yeah, not too bad, thanks. How's it going with you?
It's great, thanks. So start whenever you're ready.
Excellent. All right. Just a moment whilst I get all my ducks in a row, as it were. Shrink myself down into the bottom corner. So, hello, everyone. I'm Benjie, as previously mentioned, and I love GraphQL. I think GraphQL is awesome. It's made such a huge impact in the way that we build our client applications, our websites, our mobile apps, and more. It's shown us how we can be more efficient and get rid of this overfetching and underfetching, and really do things in a way that is highly optimized to the way that clients need. By minimizing the number of round trips and by having type safety, these both reduce the risk of something going wrong. And by handling partially successful results, it means that even if something goes wrong on the server, we can still render something useful to the user. The built-in documentation in GraphQL helps to increase productivity. And of course, by delivering the data in the shape that the client expects, we can minimize the amount of wrangling that needs to go on the client side. So all of this makes it much easier and faster to write our client applications, which makes it easier and faster to build things that our users love. GraphQL is amazing. But I have a confession to make. I hate resolvers. I've always hated resolvers. The GraphQL language is declarative. And yet, resolvers were not built to leverage this awesome capability. Instead, they turn execution into a procedural, layer by layer, field by field, item by item approach. To my mind, resolvers are very much a minimum viable product approach to execution. They're simple to understand and to specify, but they punt things like solving the N+1 problem into user space, requiring schema designers to remember to use abstractions such as data loader to achieve acceptable performance. And they rule out entire classes of optimization strategies. If you want to optimize what you're asking your business logic layer to do based on the incoming GraphQL query, for example, to only select certain fields from a database, or to tell your remote API to include additional resources that are needed, then you have to dabble with abstract syntax trees or similar look-ahead or transpilation complexities. It's unpleasant, and it's a lot of effort. Even people who put in this effort tend to only do so to a fairly superficial level. But the real efficiency gains would come from pushing this a bit further. All of this means that GraphQL is making our servers do more than they should need to, burning more CPU cycles, making more network calls, using more energy, putting more pressure on the environment, and it's not doing as much as it could be to save us money on our server bills or to reduce latency for our clients. In fact, my distaste for resolvers is actually why I joined the GraphQL working group in the first place back in 2018. The GraphQL specification seems to dictate that we must execute our operations using resolvers. It just seems so unnecessary. GraphQL being declarative language, why must we stipulate that we must execute it in a procedural manner? As I grew to learn the GraphQL specification, I realized, of course, that we don't stipulate that we must use resolvers at all. One paragraph right near the start of the GraphQL spec, which I must admit when I first read, I completely skipped over, went straight to the execution section, states, conformance requirements expressed as algorithms can be fulfilled by an implementation of this specification in any way, as long as the perceived result is equivalent. i.e., we stipulate that it must look like that's how it's executed, but that doesn't necessarily have to be what we actually do on the server side. So long as the observable result is the same, do whatever you want. but we still have resolvers. Resolvers are still the dominant way of executing GraphQL. Even in projects that delve a little deeper into optimizing backend queries, using tools such as my own GraphQL Pass Resolve Info module to look ahead and figure out what fields are being requested, we're still using resolvers. And the reasoning behind them is sound. The way they describe execution is correct. Without this definition, GraphQL could become more of a transfer format than an execution engine. Clients wouldn't be able to rely on the same assumptions, the assumptions that make things like normalized caching possible, because resolvers enforce the graph nature of GraphQL, where we traverse from node to node. The value of the node that we're on being dependent on neither where we came from nor where we're going to. And yet, this doesn't have to be the way that we actually execute operations. I've been battling this problem on and off for almost 6 years. I've tried many experiments over that time. I've really delved deep into the GraphQL specification to understand exactly why resolvers are specified, what they're protecting us from, and why are they declared in the way that they are. I tried to work within the constraints of GraphQL JS to solve this problem, and I've been reasonably successful. But it's always irked me that it just doesn't feel as ergonomic as it should be. The workarounds that I've come up with have been really clumsy and rigid. Admittedly, many of those solutions I came up with before I had the support of my many sponsors, so I couldn't really invest much time into their research. But thankfully, a lot of people have found the software that I write very helpful, and as my sponsorship has grown, thank you sponsors, the amount of time I have to invest in this problem has increased. About 2.5 years ago, I set out, very part-time, to solve this problem once and for all. But before we get into that, let's talk about my inspiration. For those of you who know me, you'll know that I love relational databases. Well, one particular relational database. Relational databases use SQL, which is a declarative language. It specifies to the server what data is required, and the server decides how to execute it. And it can choose many different ways of executing that query. For example, it could factor in the presence of indexes, or figure out how much data is expected so that it knows which type of operations to attempt to do. This is called query planning. Modern Postgres even has such things as genetic algorithms to help choose the very best possible execution plan in as little time as possible. And things like just-in-time compilation, which will compile your SQL expressions down to machine code so that they can be executed in the most efficient way possible. Now, GraphQL is declarative too. So we have resolvers. We don't have generic execution planning for GraphQL. But it's not fair to say that we have nothing. Loads of people have felt this pain. So now we have specialized planners such as the GraphQL to GraphQL planner found in Apollo Federation. Or we have optimization of the GraphQL internals in GraphQL JIT. We also have ways of optimizing particular patterns, such as projections in Hot Chocolate, or the GraphQL to SQL transpilation within Hasura. But we don't have a powerful, general-purpose query planning system that takes a holistic approach and allows advanced optimizations no matter what your underlying business logic may be, at least until now. So, after that really long introduction, I'm here today to say, step aside, resolvers. There's a new way to execute any GraphQL operation. The working title for this new project is GraphFast, and it works by taking your GraphQL operation and compiling it into an execution and output plan. Now, the output plan is a straightforward mapping from the data that we retrieve through the execution phase to the GraphQL result that we're going to output for the user. So we'll skip over that. Most of what we care about is the execution plan. We build the execution plan by mostly following the execution algorithm that is in the GraphQL specification. However, we do this before we actually execute. So we're not dealing with the concrete data that we would be in the GraphQL specification. We're instead dealing with what we call steps that represent this future data. When it comes time to execute, a step is quite similar to a data loader in that it accepts a list of inputs and it returns a list of outputs. So batching is built into the very heart of GraphFast. Whereas a field in a traditional GraphQL schema would have a resolver, in GraphFast it would have a plan resolver. The plan resolver has similar looking code as you might be able to see from a glance, don't bother reading it in detail, but again, rather than dealing with concrete runtime data, it's dealing with this future data, these steps, which we represent with a dollar symbol in the code on the right. So when we see a GraphQL operation, such as this one, we can walk through the selection sets and we call the relevant plan resolvers at each stage. And out of that, we can build a plan diagram like this one that expresses exactly what needs to happen. Now, this plan diagram is not the final thing that will be executed. This is just our first draft. The GraphQL system will go through each step in the plan diagram and give it a chance to deduplicate itself, to optimize itself, and to finalize itself. These are the three main lifecycle methods that the steps may implement. Deduplication allows for similar steps to be amalgamated to simplify our plan diagrams. Optimization is the main phase, the most critical one to performance, and it allows steps of the same family to communicate with each other and pass information between one another. For example, if we're dealing with the Stripe API, we might have a GraphQL request that has a field in it that fetches the customer from Stripe. And then maybe the user has also requested a child field on that that fetches the subscriptions for that customer, and then various fields below that. Now, when the step that's responsible for getting the subscriptions is being optimized, and remember this is before we execute, it could determine that its grandparent is pulling data from a Stripe customer, and thus tell the customer step to fetch the subscriptions at the same time. Stripe has a feature called expanding for this. This would mean that the subscriptions fetching step is now redundant. So, as a last action in Optimize, it can replace itself with a step that extracts the relevant data from the customer response. This way, we now only need one round trip to Stripe to get all the information that we require for our GraphQL operation. Finally, we have the finalize method. This is typically unused for most steps, but it gives the step a chance to prepare for execution, to do something that only needs to be done once. For example, it might be used to compile an optimized JavaScript function to execute its action more efficiently, or it might be used to prepare a final SQL or GraphQL query text ready to be sent multiple times in the future. Now, importantly, steps are designed to be something that you can implement yourself, much like you would with a data loader callback. They're a little more powerful than data loader, and they have these optional lifecycle methods that we've discussed. But in the simplest case, all they need is an execute method that takes a list of values and returns a list of values in the same way that a data loader callback does. We also have a number of optimized pre-built steps that you can use to handle common concerns, including things like load one for batch loading remote resources similar to data loader, or each for mapping over lists, or access for accessing properties from objects. And we're building out more optimized steps for dealing with particular concerns, for example, issuing HTTP requests, or sending GraphQL queries, or talking to databases. Ultimately, our intent is to use these steps to pass additional information to your business logic layer, no matter what it is, so that it can execute its tasks more efficiently. So, just like GraphQL helps to eliminate the over and under fetching on the client side, GraphFast helps you to eliminate it on the server side. For example, if your business logic is implemented with an ORM or something like that, you can use this additional information to perform selective eager loading to reduce the number of database round trips that you need to make. If your business logic is from an HTTP API, you could use this contextual information to dictate which parameters to pass, better controlling the data that you're retrieving, reducing the server load and the network traffic. And since GraphFast is designed around the concept of batching, you never need to think about the n+1 problem again. It's solved for you out of the box by virtue of just how the system works. Now, just like with GraphQL resolvers, GraphFast plan resolvers are intended to be short and only express what is necessary to communicate between GraphQL and your business logic. And despite their pleasant ergonomics, they unlock much greater efficiency and performance than resolvers can. GraphFast has been built from the ground up to support all of the features of modern GraphQL: queries, mutations, subscriptions, polymorphism, and even cutting-edge technology such as stream and defer. And it's backwards compatible with existing GraphQL schemas, so you can use GraphFast to execute requests against an existing resolver-based schema, and then migrate to plan resolvers on a field-by-field basis. And if you're already using data loaders, then migrating to using GraphFast plans should be quite straightforward. We're hoping to release an open source version in the next few months. It will be under the MIT license, as is all of my open source work. To be notified when we're ready for that release, please enter your email address at graphfast.org and we'll send out a mailing list shot when the time comes. If you'd like to help me to continue to invest time in projects like this, then please consider sponsoring me on GitHub sponsors. And you may even get early access. Feel free to reach out to me with any questions. Thank you for your time, and I hope you're as excited about the future of GraphQL as I am.
Right. Thank you, Benjie. Great talk, and it looks very interesting. So let's see if we have any questions. Yeah, I'll just add that we have really cool merch t-shirts from GraphQL Wrocław. So for every question, we give one t-shirt. Yeah, nice. I know. So are there any questions? Come on, don't be shy. Yeah.
Free t-shirt. Just for the t-shirt. Yeah, it looks amazing. So I was wondering, so it seems like the resolvers are essentially lazy, right? So every function is not actually querying the data, it just creates like a lazy function that gets queried at the very end, right?
It's a little bit more complex than that. So it builds out these steps, which are, so that code, those plan resolvers, that code doesn't run at execution time. It only runs once at planning time to figure out what steps are involved. And then after that, then the steps themselves execute, which is different code.
Yeah. So this is what I mean. Like essentially, these are just a bunch of lazy objects. And what happens if you resolve something and you actually in that chain you actually need the data of of the parent to be able to resolve the children, because the data is not being fetched at that moment, and you have that dependency that you actually need to know. What would be this? How would the strategy look like then?
Okay, so I think what you're asking is if you need to branch during the plan. So
Yeah.
if based on the data you fetched, you might take one action or another. There are a few ways that that may happen. So for example, polymorphism is a good example of that. If you fetched a user, then you might need to do user things. If you fetched a cat, you need to do cat things. So that's all baked into the system. However, what you should probably keep in mind is that this isn't intended to replace your business logic. This is built on top of your business logic in the same way that resolvers should be in GraphQL. So it's only meant to be a thin layer. All of your branching should really be mostly in your business logic, and it shouldn't generally be a concern. There are, however, things where you might want to branch based on the user input to your query. So things like input arguments. You might want to, for example, filter the a field to say only include the users and don't include the cats, in which case, the SQL queries or whatever you've got on your backend is going to be different. And we do allow you to branch the plan based on user input. And that's not done as like a exact value match. It's done as a kind of a broad match, as broad as you can allow it to be, and still meet your requirements. So there is branching based on user input.
Excellent. Thank you.
Thank you. You earned a t-shirt. So, any other questions?
Sorry. This optimization of the queries, it happened on a SQL level or just like a higher level in JavaScript, in like when it analyzes what you're trying to do, but like how would it know that it need to make like one query to SQL or multiple?
Okay, so the steps themselves, the step classes, so you can think of them a little bit like data loaders. They have that logic in them. GraphFast doesn't do that for you. All it does is it tells them to do it. So each of those steps, it says, it's your turn to optimize. You go do your thing now. So you have effectively like families of steps. We're building some for you. So like we've got some that are highly optimized for talking with Postgres, of course, because of PostGraphQL. And there's things like the load one that you can use in a data loader like sense. But when you've got your own business logic, you can build your own steps that have their own optimization strategies that understand your logic and what your kind of inlining is. And one of the best things about this is you don't need to add those optimizations at the very start. Instead, you can just build out with a basic set of steps that just do the work. And when you want to later optimize them, you just update the step definitions. You don't have to update your schema code or your plan resolvers, just the steps themselves where they have those lifecycle methods. And you can give them the ability to talk to each other and to make decisions. So for example, we talked about the Stripe example in this. That would be something specific to Stripe. So it would probably be a family of Stripe-related steps.
Okay, then I need to build like based on my application, I need to build these steps. And then in these steps, I need to build a family of steps. And then the optimizer would know how to optimize my steps based on how I define them.
Yeah, you define your own optimization strategy for each step. Or you don't, that it's optional. At a baseline, it will be the same as just having a data loader. But if you want to implement optimization over it, then you can unlock this greater ability. And I suspect what we'll see is a lot of like user contributed steps. So for example, I hope that we'll see like a Stripe family of steps that people can use if they need to communicate with Stripe and things like that.
Thank you. Any other questions? If not, then I have one. Like I was wondering how it works, like when you want to integrate GraphFast with your server. So is this actually behaving as a GraphQL server? So you use that instead of the server you use normally, or is this some kind of middleware or a library that you plug into your existing code? Like, yeah.
Great question. So GraphFast at the moment is implemented in JavaScript. My intention is that it will be implemented in many languages in the same way that GraphQL is. I would like to see resolvers go across the board. But at the moment, it's effectively a replacement for the execute method that we have inside of GraphQL.js. So GraphQL.js has a GraphQL method. What that GraphQL method does is it passes the query, then it validates the query, and then it executes the query. So we are just, GraphFast is a replacement just for execute.
All right. Yeah, I was wondering actually about the support in other languages. For example, we use Python and Graphene. So I suppose that in the future you would like release some kind of specification of how is that built, and then, for example, the community could build Python support for that, which we could use in Python frameworks, for example.
Yeah, absolutely. I'd love to do that. And I think one of the great things about this is because it only really covers the execution section, it should be hopefully relatively easy for other languages to adopt. They don't need to redo all of their validation and various other things. It's literally just the execute section. And I'm really interested to see at some point how this will work with other languages. So for example, Python, I know you've got things like twisted Python, right? I think, which handles like asynchronous, there's like promises and stuff like JavaScript does.
Yes.
But Python itself is generally a synchronous language. And I think GraphFast would actually lend itself really nicely because of the way that it does batching, and it doesn't rely on these kind of parallel promises that the GraphQL spec itself kind of does. It should make support for those kind of languages even easier, I hope.
Yeah, really looking forward to having support for that in Python. So maybe one last question, since you are part of the GraphQL working group, maybe you can say something like a little about it, like what you are like working on right now, what's like maybe the main focus of the working group right now. Is there any specific feature that you are focused on? I know this will be part of Michael's talk, but maybe there is something that you are personally involved or happy about, like some new feature coming to GraphQL.
Okay, well, I'll cover, so as to not steal too much of Michael's thunder, I'll cover two things. One is that the bulk of work, I would say at the moment, like the busiest, most active part is on the stream and defer directives. Defer particularly, but also stream. And we're doing a lot of work, and we're actually doing weekly meetups now to discuss those features, to try and help get this over the line so that we can actually merge it into the spec. We've actually got quite a number of experimental implementations out there, but because we keep changing stream and defer itself, like it's not ready to go into the main master spec just yet, but we're getting quite close now, I think. As for things that I'm involved with that, but only in a peripheral sense. I'm also the author of the one-of RFC. So one-of is a directive that you could add to input objects to say exactly one of these keys should be set and must be non-null. What this is really saying is it's giving you a way to do polymorphism on input, which we don't really have currently in GraphQL. So we spent a lot of time, we've actually been talking about this for almost 3 years now, I think, talking about the various different ways that we could introduce polymorphism in the input of GraphQL. And there have been a lot of approaches, some of them that look a lot more like the interfaces and unions you may be familiar with from the GraphQL spec itself. But it turns out that they're not always the best match, and actually a different approach for polymorphism on input might make more sense. So I wrote the one-off proposal and pushed it a fair way along, and it is currently the favorite. But after doing that, I came up with another idea, which I'm calling the tagged type. And that, no, it's a different one. I've forgotten its name. But that one is thinking more in terms of solving this problem, but also solving some other problems. It's called struct, my apologies. So struct is giving the ability to have like structured leaf nodes in GraphQL. So where you request a leaf, you normally receive the whole thing, like an int or a float or a string, something like that. You receive the whole thing. This is giving you the ability to have a leaf that is structured. So you can just say, I want this thing, and you get the entire document come through. It could be like a prose mirror document or something like that. That is one that I am exploring, and it has meant that I've put one on hold a little bit because I want to explore the struct type a little bit more first before we commit to one or the other. Because one of the things about the GraphQL spec is we want it to keep working, you know, indefinitely into the future. And we don't really want to say like, oh yeah, we introduced like 8 different forms of polymorphism, because that's going to be a bit overwhelming. So we'd like to get it right first time if we can.
Sounds really nice. So are we going to just add that to the spec, or is it like the plan to release some GraphQL v2 or something like that? Or are those new features just rolled out in the spec and then like server maintainers, it's like their turn to implement that? Is that like how it works?
Yeah, so everything we put into the spec at the moment is backwards compatible unless there is a really, really good reason that it cannot be, and where, you know, very few people would be affected by these changes in a negative fashion. So everything is additive. In the same way that when you write your GraphQL schema, you should make additive changes to it so that it still supports all of your older clients. We want to support all of the GraphQL clients across the world in, you know, Relay and Apollo and Urkel, and but also all of the little like fetches that you've got in your shell scripts, all that stuff. So yeah, we're very, very careful, and this would just go out as a normal feature in GraphQL, so it wouldn't be any kind of major version bump. We don't even have the concept of like a major version bump. We do have releases, but they're more just like a, you know, a chance to announce, hey, we've done these things. Really, you've been able to use them for like 6 months, 12 months before we do one, really.
Okay, cool. I don't have any more questions. Anyone else, maybe? If no, then thanks a lot, Benjie. It was great having you. A lot of good stuff here, so thanks a lot.
Thanks, everyone.